So now we're going to talk about the chain rule. So we've technically been using this for derivatives, but because we have this kind of hierarchy of variables, we know the chain rule was useful for composite functions. Well, now because I've got multivariable functions, if you have inner working layers, it's a little more complex to figure out what's going on. So we're going to look at a different approach for how we can find derivatives and partial derivatives. And what I'm going to do is I'm going to start just with our Calc 1 knowledge. So suppose we know that y is a function of x, but ultimately your x was dependent upon another parameter, t. Okay? So in the end, your y is a function of x, but x is a function of t. Okay? So in the end, the final dependency was y dependent on t, but you have to go through this intermittent variable x. Okay? It's exactly what we did when we were talking about parametric equations. So if both f of x and x of t are differentiable, then ultimately y is a differentiable function of t. Specifically with the following. Okay? So if I want to take the derivative of y with respect to t, I first have to go from y through x, and then I go from x to t. And so if you remember your parametric equations, if you were finding the first derivative, it was dy dt divided by dx dt. Okay. What's actually really helpful for this is drawing a different type of diagram, which is called a tree diagram. So it's kind of showing us the layers with these variables. So our topmost variable is y, and that depends on x. And then x depends on t. So ultimately, you have y depending on t. This first branch is the derivative of y with respect to x. And then the second branch is the derivative of x with respect to t. So if I want the derivative of y with respect to t, I just go ahead and multiply the things along that particular path. Okay? So it'll make it much easier when I have multivariables and a lot of layers going on. Right? But in the end, I have a single variable dependence. T is at that bottom layer. And really, each level is just a single variable. So the problem is when we've got multivariables, there are a ton of different cases and versions. So we're going to go with a more general case. We'll call this version 1 or case 1. And so this is going to be just when we have a function of x and y, and then both x and y depend on t. So suppose that z is a function of x and y, where x is a function of t, and y is also a function of t. Then ultimately, z is also a function of t. And we can figure out how to take that derivative. Okay. So to give us a little diagram, we have z sitting up here. That depends upon two variables, x and y. And then each of these is dependent upon t. So ultimately, we have single variable dependence. So this is where you have to be really careful with partials versus that d operator. So what I can do is I can actually take the derivative of z with respect to t. Okay? Because that first layer and last layer are single variable dependence. However, I have two paths to get down to this variable. I've got this first path, and then I've got this second path. So what I'm doing to find my derivative is I'm going to figure out the magnitude basically of this path, the magnitude of this one, and add them together. So for this first branch right here, because this layer is multivariable, this first branch is the partial of z with respect to x. While over here, same thing, because that second layer from z to x and y has that multivariable dependence, this branch is the partial of z with respect to y. Okay. But then down here, this is single variable dependence, so this would be the derivative of x with respect to t. And then likewise right here, y just depends on t, so it's the derivative of y with respect to t. Okay. So traveling down my first path, the first branch is the partial of z with respect to x. And then the second branch is the derivative of x with respect to t. Now I'm going to add the second way I get down to that variable, which is this second path. And so I need to go from z to y, which is a partial, and then I need to go from y to t, which is a normal derivative. Okay. So I'm going to show you two different ways that you can go about calculating a derivative like this. It is completely up to you which version you want to do. However, you want to make sure that you are comfortable writing diagrams or tree diagrams and writing out derivatives like this. So this way you can see that dependency. So let's try an example. Let's find dz dt if z is arctangent of y over x with x equaling e to the t and y equaling 1 minus e to the negative t. So again, if I draw this tree diagram, z depends upon x and y, and then each of these are single variable. Okay. So I've got to start by finding the partials of this thing. I need the partial with respect to x and the partial with respect to y. And then here I've got full derivatives. Okay. So starting with the partial of z with respect to x. Derivative of arctangent is 1 over 1 plus x squared. So in this case with my multivariable, I get 1 over 1 plus this thing squared. And then chain rule, I've got to take the derivative of this thing with respect to x. So just to rewrite this, this is yx to the negative 1. So if I go through, this is 1 over 1 plus, I'll write this out as y squared over x squared. Derivative of this with respect to x, we bring that power down, decrease it by 1. So that's negative yx to the negative 2. Okay. And then I'm going to even rewrite this in here so it's nicer. That's y over x squared. If you left it like this, that's not a problem, but I'd rather clean this up so it's not as complex looking. So when we multiply fractions, we multiply across. So that's negative y in the numerator. And then here I would take this expression and times it by x squared. So 1 times x squared is x squared. And then luckily when I take this and times it by x squared, that makes the x squared cancel. So it becomes much simpler. Okay. Now I also need to find the partial with respect to y. Okay. So luckily it's the same starting piece. It's 1 over 1 plus this inside squared. The only difference is I'm now taking a derivative with respect to y of this. And thankfully this is a little bit nicer because the derivative of y is 1. So this ends up being just 1 over x. Okay. But I would really like if the denominator simplified to something a little bit better. So instead of an x, I would really like an x squared to make that piece cancel. So I'm going to go ahead and I'm going to multiply this by x over x as well. Because what that does is it gives me an x in the numerator, but then you're multiplying by x squared in the denominator again. So it cleans up super nicely. Okay. So now I've got this first layer done. I need to find the second layer. And thankfully that's much nicer. I'm going to go ahead and take the derivative of both of these with respect to t. And those, again, are going to be full derivatives. So the derivative of x with respect to t is thankfully just e to the t. And then the derivative of y with respect to t that's going to be 0. This, you get a negative sign that pops down to make this positive. So it becomes e to the negative t. Okay. So I have all 4 branches along my paths. So now I can go ahead and find the derivative of z with respect to t. We first have the partial of z with respect to x, and then x to t, and then z to y, and y to t. Okay. So filling in each of these pieces, this is negative y over x squared plus y squared. Dx dt is e to the t. And then partial of y with respect, or partial of z with respect to y is x over x squared plus y squared. And then the derivative of y with respect to t is e to the negative t. Okay. This perfectly fine on your written portion of a test. Okay. Just double checking your homework software, it might want you to solely write this in terms of t. And if that's the case, it's really not too bad to do. All you're going to do is, in place of all of these x and y's, you plug in these variables here. So y is 1 minus e to the t. So this would be negative 1 minus e to the negative t. The denominator x is e to the t. So this is e to the t squared. and that is 1 minus e to the negative t squared, e to the t. So again, the y getting replaced by 1 minus e to the t, and then the x is getting replaced by e to the t. Same thing for the second piece, x is e to the t, and then luckily the denominator is exactly the same here. So x got replaced by e to the t, and y got replaced by 1 minus e to the negative t. So this would be your full derivative solely in terms of the variable t. Okay. What I'm going to do is I'm going to go show you a second way to go about this problem. And again, it's completely up to you. What you can also do, I'm not going to actually calculate this derivative, but you would get the same thing, is your z is arctangent of y over x. Well, y is 1 minus e to the negative t, and x is e to the t. So you can pretty much just rewrite z completely in terms of t, and now you would just take your normal derivative. Personally, I think this way is going to be 10 times worse, especially in more complicated situations. Because you can see you have a function inside of a function. So I would have to start by going through my chain rule. So I differentiate the arctangent. It would be 1 over 1 plus this thing squared. Then I would have to take the derivative of this, which is going to require quotient rule. And if I've got multivariable functions still at the end, I'm then going to have to take a lot of partials going on. It will result in the same thing, but it's going to be a lot more work when we get more complicated problems. Okay? But again, up to you, but you still want to be confident in writing out those tree diagrams and writing out the equation for the partials or derivatives, whatever they may be. So let's look at a second case of chain rule. And this is where our z is still going to be a multivariable function, so it's going to depend on x and y. But then x and y are also multivariable functions that depend on s and t. So we have multiple layers going on. So here, suppose z is a function of x and y. Suppose this is a differentiable function. Where x is really a function dependent upon s and t, and y is the same thing. It is dependent upon s and t. And these are differentiable functions of s and t. Then we've got the following. So starting with my tree diagram, c is my topmost variable, and I'm going to need some bigger space here. It depends upon two variables, x and y. Okay. Then each of these have multivariable dependence, s and t. So ultimately with this, I'm going to be taking partials of z with respect to s and t because I've got multivariable dependence. Okay. So if I want to get down to my derivative with respect to s, I've got, again, 2 paths that I have to take. And then likewise, if I want to get down to t, I've got 2 paths that I have to take. So this first layer is going to be partials of z with respect to x or with respect to y. And then here, these are both going to be partials as well. This is partial of x with respect to s, and the partial of y with respect to s. And then these last little branches are partials with respect to t. So if I want to take the partial of z with respect to s, I first have to go through x, and then from x to s. And then I've got a second path down through y, and then y to s. And likewise, if I want to find the partial of z with respect to t, I can go ahead and go through x, and then x to t, or I can go through y. Okay. So let's try an example of this one. We're going to let z equal e to the x plus 2y, specifically with x being s over t and y being t over s. We're going to find the partial of z with respect to s and the partial of z with respect to t. So again, I always like to start by doing my branches. Z is our top one. It depends on x and y. And then x has both of these variables, s and t. So I'm just going to find all of the pieces that I need. We'll start with dz dx, the partial of z with respect to x. Okay. So e to anything is e to anything. And then when I take the partial with respect to x of that exponent, it is really just 1. So I'm going to go ahead and just erase this. Then we also need the partial of z with respect to y. And same thing, you get exactly the same exponential, but chain rule tells us I got to take the derivative with respect to y. So all that ends up happening is we get a 2. So I'm really just going to put that out front. This is 2, e to the x plus 2y. Now for both of these, I'm going to have to go ahead and take both partials. So I'm going to rewrite it slightly to help me with each one. If I start by the partial of z, or sorry, not partial of z, partial of x with respect to s, well, that's s and then divided by t. So really you just get 1 over t because derivative of s is 1. If I take the derivative with respect to t, that's where I'm going to have to use my power rule. So bringing the negative 1 down, decreasing that power by 1 gives us negative s over t squared. Doing the same thing now with y, partial of y with respect to s. Since it's s to the negative 1, bring that 1 down, and then you get s to the negative 2, so it is negative t over s squared. and then the derivative of y with respect to t is, thankfully, a derivative of this is just 1, so you get s to the negative 1, which is 1 over s. So I have everything I need now to go ahead and find my two partials that I'm looking for. So my first path is through x, and then from x to s, and then the same thing, I go through y, and then y to s. So filling in each of these things, first piece is e to the x plus 2y, and then partial of x with respect to s is 1 over t. And then here, this is 2e to the x plus 2y, and partial of y with respect to s is negative t over s squared. Okay. Leaving like this, perfectly fine on a test, but again, just pay attention to the directions. You might have to replace x and y by these to get it fully in terms of s and t. Then for the next partial, with respect to t, we do the same thing, but now anywhere I see an x, it's getting, or an s, it's getting replaced by a t. So really not much changes except for these two pieces. So these ones are just going to get replaced by these two. So this partial derivative is e to the x plus 2y times negative s over t squared. And then we've got 2e to the x plus 2y times 1 over s. So realistically, the more complicated I make this, it doesn't change a whole lot. If you draw that T diagram or tree diagram, you can figure out the type of dependence you have and whether you can use a partial versus a full derivative. And then you just follow the paths down to the variable you're looking for the derivative of. So you can look in the book or the notes that I have posted for the general case of this, but again, just for time's sake, I'm just going to do some more examples and show you how you go about other cases of chain rule. But you can look at the most general one there. So let's try this next example. Let's let w equal 1/2 natural log of x squared plus y squared plus z squared. X is going to be sine of t. Y is cosine of t. And z is tangent of t. Based on this, we want to find the derivative of w with respect to t. So starting with my tree diagram, w is going to be my highest variable, and it has dependency upon x, y, and z. So that's what our first function tells us. But now looking at x, that has single variable dependence upon t. Likewise, y and z have single variable dependence upon t. So ultimately, in the end, we have that single variable dependence, which is why we're able to take the derivative of w with respect to t. So this first layer is all going to be partial derivatives. And then the second layer is just our normal derivatives. That's where we can use the d over dt. So my equation for the derivative of w with respect to t is going to be my first path is through x. So I start by taking a partial with respect to x, and then from x to t. So this next one is then dx over dt. Second path is through y and then to t. The first one is a partial, and then it is a full derivative. And my final is through z to t. The first is a partial, and then the second is a normal derivative. Okay. So all I need to do is fill in each of these derivatives. I think these three you're confident in just taking a derivative of. Hopefully you remember your natural log. The derivative is 1 over the inside function. And then chain rule, you'll just have to take the derivative of whatever variable. So this one I'm just going to jump into. So the first one, derivative with respect to x, is we get 1 over the inside. So I'm just going to write the inside out. The derivative of the inside is just going to be 2x. But the 2 is going to cancel with the half. So we really just get the x out front. Then if I look at dx dt, derivative of sine is just cosine of t. Okay. Now we do the same thing, but now I'm going through y. And thankfully, this is going to really be the same for each of them, just a different variable in the numerator. Because I'm going to get 1 over the inside, and then chain rule, a 2y gets attached. So the 2 and the 1/2 cancel. So this derivative is y over x squared plus y squared plus z squared. And then the derivative of cosine of t is going to be negative sine of t. I'm going to move this up so I don't run into it. And then for my last stage, the derivative of w with respect to z is now the same, but you get a z in the numerator. And then we have to take the derivative of z with respect to t, so it is secant squared of t. And so this would be my derivative of w with respect to t. Again, I can just replace x, y, and t by these, and that would be a then single variable function. So I got one more of these before we do implicit differentiation. We're going to let z equal xy squared. X is going to be rs plus t. And y is st. We're going to find three things. The derivative of z with respect to r, with respect to s, and then with respect to t. Okay. So drawing my tree diagram, z is my topmost variable. It depends upon x and y. And then x depends upon three variables, r, s, t. Y depends upon two variables, s, t. Okay. So I'm going to start by actually writing all of the different partials first, and then I'll kind of go back and fill in the pieces. But this is a relatively short one. So in the end, I do have multivariable dependence. So we are taking partials. So starting with our first one, we'll do the derivative, partial derivative of z with respect to r. If I follow my pass down to r, get it a little bit thicker, I really only have one way to get there, which is kind of nice. I don't have to go through y either. So this will be the partial of z with respect to x, and then x to r. Everything is partials. Okay. If I then want to find the partial of z with respect to s, I have two different paths down there. I go through x, and then I also go through s. So this is going to be the partial of z with respect to x, and then x to s. Or I can go through y, and then y to s. And then finally, to get to t, I really have the same kind of way. I go through x or I go through y. So the partial of z with respect to t is pretty much the same as above, but replacing s by t. So we go through x, and then we get to t. Go through y, and then we get to t. Okay. So all I need to do is find all of these partial derivatives, but luckily these are all just polynomials up here, so the partials aren't too bad. So let's find the partial of z with respect to x. And luckily, the derivative of that is 1, so you just get y squared. And then the partial of z with respect to y, derivative of y squared is 2y, so this is 2xy. Then I've got to differentiate all of these variables with respect to rs and t. So we'll start by doing x. Partial of x with respect to r is just going to be s. Partial of x with respect to s, in this case, is r. And then partial of x with respect to t is going to be 1. Doing the same for t, you can, or the same for y, you can technically do the partial of y with respect to r. It's 0, which is why it's just easier to just not draw a branch, because then I don't even have to worry about it. Partial of y with respect to s is going to be t, and then partial of y with respect to t is s. So again, derivative of each one separately is just 1, so you get the other variable. So filling in now each of the pieces, I'll go ahead and kind of just highlight stuff. Partial with respect to x, all of these are going to get replaced by y squared. And then all of my partials with respect to y are going to get replaced by 2xy. And then we're just filling in these pieces as needed. So I'm going to avoid highlighting those. So this first one would be y squared times s. This next one will be y squared times r plus 2xy times t. And then here, partial of z with respect to x is y squared. Partial of x with respect to t is 1. And then partial of z with respect to y is 2xy. And then the partial of y with respect to t is s. So these are our different partial derivatives. So now we're going to go through and we're going to see a different way to do implicit differentiation. So I'm going to show you two different cases of this. The first one being our Calc 1 approach, and then the second one being now with implicit differentiation of multivariable functions. So this first case, we're going to assume that we have a function of x and y, and again, it's some relationship, so you can't solve for one of the variables. But what we can do is we can move everything to one side to guarantee that we have some expression equaling 0. So suppose that we have a function I'm going to call capital F of x and y equaling 0. And this is where we have a dependency that y is some function of x. Okay. Then what we have going on here is we have this function capital F that's dependent upon x and y. And then we have this extra layer that's y is dependent upon x. And you can put another branch here if you want. X is dependent just on x itself, but realistically you don't actually need this here. Okay. So if I want to take the derivative of both sides with respect to x, which again we can take a solid derivative because it's that single variable dependence, which is why it might be nice for you to put that x here to see single variable dependence. Then we're going to take the derivative on both sides. Okay. At least on the right, this thing is just going to be 0, which is great. And then on the left-hand side, we have two cases. We first go through x and then down to x again. But again, this branch doesn't do anything. And then our second case is we go through y and then y to x. Okay. So the first thing we do is we take the partial of f with respect to x. So that's this first branch right here. And then I go from x to x itself. So this is the piece that's kind of useless. This right here is just 1. Okay. Then our second route down to x is from f to y. And then from y to x. Okay. And remember, your whole goal with implicit differentiation was you were solving for this piece. So just to make things a little bit simpler, this is saying take the partial of f with respect to x. That's the partial of f with respect to y. And then we've got the piece we're looking for. So solving for dy dx, we go ahead and just subtract this and then divide by this. So we come up with actually a simpler formula. The derivative of y with respect to x is really negative the partial with respect to x divided by the partial with respect to y. Okay. So if I have now a multivariable function, I can do exactly the same thing, really. So let's see the other case, and then we'll try an example. So suppose that now we have triple variable, an expression involving x, y, and z equaling 0, where z is a function of x and y. Okay. And then again, I might be concerned with what is my partial derivative through implicit differentiation. So I could take a derivative of both sides with respect to x or with respect to y, and then I would have to do a bunch of partials and then solve for the partial I'm specifically looking for. But I can come up with another nice formula that's just like this one. So instead, I've got my function f. It's dependent upon 3 things, x, y, and z. And then z has another layer. It's dependent upon x and y. These have no other dependencies, so they just get brought straight down. So if I go through and I take the partial with respect to x on both sides, again, on this right-hand side, this is nice. That's just going to equal 0. And then in this case, if I want to get down to x, I go through x itself, or I go through z. So applying my chain rule, this would tell me take the partial of f with respect to x, and then x to itself does nothing. Or I do the partial of f with respect to z, and then from z I go down to x. And again, making these nicer notations, this is f sub x, this is f sub z, and then this is that thing I'm looking for in implicit differentiation. So just going through and solving for the partial of z with respect to x, again, you would subtract f sub x, and then you would divide by f sub z. So we get a much nicer formula to work with. Okay. And then realistically, instead back here, I could have taken the partial with respect to y. The only difference that would happen is these would be y's, and so these two things would be y's. So in a similar manner, or in the same manner, if I want the partial of z with respect to y, it would be negative f sub y over f sub z. Okay. So in practice, completely up to you what you want to do when you take, or when you have to do implicit differentiation. I'm going to show you both methods for a Calc 1 problem because I think the Calc 1 version is easier to see in our old way. So I'm going to scroll, new page, make it nice. So given that cosine of xy is 1 plus sine of y, we're going to find dy dx. And method 1 is going to be the Calc 1 way. So what I would need to do is on both sides of these equations, I've got to go ahead and I've got to take a derivative with respect to x. So I'm going to give myself a little bit of wiggle room out front. But I'm going to take this side and I'm going to differentiate with respect to x. This side, differentiate with respect to x. And anytime I take a derivative of y, you get that dy dx attached to it. So here, going through my first derivative, I'm going to start from the outside in. So derivative of cosine is negative sine. And then chain rule, I've got to take the derivative of the inside. On the right-hand side, derivative of 1 is 0. Derivative of sine is cosine. And then again, this is where our process comes in. I'm taking a derivative of y with respect to x. So chain rule tells me that dy dx pops out. Okay. Now I've got this one last derivative to figure out first. But unfortunately, I'm going to have to do product rule because it's one function times another. So we get first, derivative of the second is 1, but it gets a dy dx attached to it. Then derivative of the first is 1, and that gets a y attached. And then on the right-hand side, we have the same thing. Okay. And now, the last thing I need to do is I need to solve for dy dx. That's my goal. What does this equal? So I've got to go ahead and I've got to distribute this negative sine of xy. So I'll put the x out front. This is x sine of xy times dy dx. And then that becomes minus y times sine of xy. And this equals cosine of y dy dx. Okay. So I'm going to go ahead and move this to the other side by adding it. So I'm left with negative y sine of xy. And then I've got cosine of y dy dx plus x sine of xy dy dx. Then, because these both have the dy dx in common, you go ahead and factor it out. And then you would go through and divide by what's left over. So immediately that tells me dy dx is going to be negative y sine of xy all over cosine of y, oh, that's a terrible y, plus x sine of xy. Okay. All right, so that's method 1. That's the way you're used to from Calc 1. Now what I want to do is show you using chain rule that we just learned. So method 2 is just by moving everything to one side to get the function equals 0. And then from our tree diagram, we get dy dx is negative partial with respect to x divided by the partial with respect to y. And I should end up with exactly the same result. So just copying down what we had to start, this is cosine of xy is 1 plus sine of y. I just want to move everything to one side. So completely up to you. You could move both of these over. You could move this to the other side. It honestly makes no difference whatsoever. So I've got one way in my notes. I'll do the opposite side here. I'll move the cosine over. So this gives me 1 plus sine of y minus cosine of xy. So what that means is my function of x and y is 1 plus sine of y minus cosine of xy. So all I'm going to do is I'm going to take the partial of this with respect to x and the partial with respect to y. So I take the partial with respect to x. This is 0. This is 0. And then here I'm going to have to do a little bit of work. Derivative of negative cosine is positive sine. And then chain rule, I've got to go ahead and take the derivative with respect to x, which is a partial of xy. Okay. And so thankfully, at least, that's just a polynomial. Derivative of x is 1. So this is really sine of xy. And then we get times a y. Okay. And then I need to take the derivative with respect to y. So going through that, derivative of this is 0. Derivative of sine of y is cosine of y. And then working with this one, same thing. I'm going to have to use chain rule. So derivative of negative cosine is going to be positive sine. Stays evaluated at xy. And then chain rule, I've got to take the derivative with respect to y. So this gives me cosine of y plus x sine of xy. And so if you go back here and compare the pieces, y sine of xy, that's exactly that. Cosine of y plus x sine of y is exactly this. And then the minus sign just comes from our formula. So ultimately, the derivative of y with respect to x is negative y sine of xy over cosine of y plus x sine of xy. So same result, completely up to you as to what's easier. I'm not going to make you memorize a formula in any way, shape, or form, but I think just ultimately taking some partial derivatives is a little bit cleaner. It's less algebra that you end up having to do, but the preference is yours.